Alright, this is going to be another Codeforces editorial, round 898, div 4 from a couple of days ago. Contest ID 1873. As usual, I'm going to gloss over the problem statements and assume that anyone watching this has read and understood the problem statement. These solutions might not be 100% optimized, but I think they're really intuitive and easy to follow. So, first problem, short sort. Brute force is an option since there's only 6 possible strings. They're actually all here. But I'll show a different way. So, either the string is already sorted, all 3 characters are in place, 1 character is in place, or none of them are in place. So if the string is already sorted, obviously we can sort it, we're done. If 1 is in place, the answer is also yes, because we can just swap the 2 that are not in place, and then all 3 will be in place. And if none are in place, then the answer is no, because we can put 2 in their place, but or we can put 1 in their place, 1 in its place, but we won't be able to put the other 2. So all we need to do is check if there's at least 1 character in place. So if any of these are true, 1 character is in place, we return yes, otherwise no. So we can do that constant time, constant space, don't need to store anything. Except the string, which is fixed sized. Okay. Problem B, good kid. So an observation that we need to realize is that we should use our increment, our 1 increment, on the minimum value in the array. A brief explanation of this strategy: if the minimum value is 0, obviously we should use it on the 0, otherwise our product will be 0. If it's not 0, when we choose a value to increment, we're increasing our final product by the product of all the other elements. So in this example, if we increment 2, so before we increment anything, our product is 4 times 3 times 2, so 24 times 12. That's 288. So if we increase this to 3, then our product goes from 288 to 4 times 3 times 3 times 3 times 4, which is 432. So it increases by the product of all the other numbers. So 4 times 3 times 3 times 4 is 144. So it increases by 144. If we increment the 3, then we increase our product by 2 times 3 times 4 times 4. So that's 96. Increment the 4, we increase our product by this amount, which is 6, 18, 72. So we want to put it on the minimum. So when we iterate over from left to right, what we're going to do is we're going to keep track of the minimum element, because that's the element we need to increment, and we're also going to keep track of the number of zeros, because if there's more than 1 0, then our answer is going to be 0 no matter what we do. So we iterate over the array, keep track of our number of zeros, keep track of the minimum element, as well as our running product. That way we don't have to, once we increment the minimum, we don't have to go back and find the product again. So if there are no zeros, so if minimum is greater than 0, it means we don't have any zeros. And our product is going to increase by the product of all the other elements. So PR is the product of all the elements. So PR divided by min is the product of all the other elements. And that's what our product will increase by, which is what we showed earlier. Otherwise, if we have more than 1 0, our product is going to be 0, because we can increment one of them, but then we'll still have another 0, so our product is 0. If we get to this case, it means we have exactly 1 0, which means that we increment it to a 1, and then our product is still the same as it was, because when we calculate our running product, we don't include zeros, otherwise it would just become 0. So if we get to this case, it means the product of all our elements except for the 1 0, and when we turn that to 1, it won't change our product. So We can do this in O of n time, although it should be noted that n is bounded by 9, so O of 1 pretty much, and then O of 1 space, since we don't actually store the array. By keeping track of the minimum and the running product, we don't need to store the actual array. So constant space on there, which is nice. Although, since the array is small anyway, storing it wouldn't be a big deal. Okay, problem C, target practice. So we can see that for any spot on the target, its corresponding locations of the 3 quadrants have the same score. So what I mean by that is if we take, maybe I should do this. If I take the target like this, and I take like this point here, if I mirror it across the 2 axes, so that all these points have the same value. That's easy to see. No matter which point it is, if I mirror it across all the axes, it will be the same. So here, the mirror on this side would be here, the mirror on this side would be here, and here. Here would be like this. So this applies to any point. So for any point in any quadrant, so we're going to use this quadrant, the top left, quadrant 2. If we have a point outside of quadrant 2, we can convert it into like its mirror image point in quadrant 2, like a corresponding point in quadrant 2 that will have the same value. That'll make it easier to compute if we only have to worry about this. So if a point is in quadrant 4 down here, it has to be mirrored across the y-axis and the x-axis to get up here. If a point is in quadrant 3, it needs to be just mirrored across the x-axis. If a point is in quadrant 1, it just needs to be mirrored across the y-axis. So I'll pull up the code so you can see the math behind that. So this helper function not only mirrors it, but then it uses the mirror to calculate the score. So this is the mirror part, and you can work out the math to see how this works. And then this is the actual score part. And the reason why that works for us is because if we just take the top left part of the target, so we've turned any point in the other 3 quadrants into a point in this quadrant. So we have only this quadrant remaining. So it's easy to see that, okay, this arc is 1 point, this arc is 2 points, this arc is 3 points, this arc is 4 points, and then this middle part is 5. And it's easy to calculate which arc we're in. We just take the minimum of our row and column. So if we're in the first row or the first column, that's what this arc is. First row, first column. If we're in the second row or second column, we're in the second arc, and so on and so forth. So that's how you get the number or the score value of any point on this target, no matter where it is. We convert it into, we map it to some point in this quadrant, and then once we get it into this quadrant, it's easy based on the arcs on the target. So we just simply iterate over the target, 1 row at a time. Then we go on this row, we go 1 column at a time. If there's a hit on the target, we add the score for this hit to our sum, output the sum at the end. Pretty simple. O of 1 per point, but we have to scan the whole board since the board size is constant, 10 by 10. Our total time is technically O of 1, but if the target was a different size, it would be however large the board is. That would be our runtime, since we have to we have to check the entire board for hits. Space is O of row size, so technically still O of 1 here, since we're reading in one row at a time. Technically O of 1 since the row size is fixed to a constant. Okay. Fourth problem, 1D eraser. So we can work on this problem greedily. So our strategy will be whenever we see a black tile, we have to erase it. But since we can erase any k consecutive cells, we may as well erase the next k minus 1 tiles. So an example, I'll draw the example from the first test. So it's 6, size 6, so 1, 2, 3, 4, 5, 6, and then this one is black, this one is black. So what we do is we start here, that's white, so we don't have to erase it. This is black, so we can erase this one, but since we can erase k, so k is 3, we may as well erase this too, just in case they were black, because we're already using an erase on this one, so we may as well erase these two in the meanwhile. But instead of erasing them, we can just skip ahead to looking here, because if they're white, then it didn't matter, and if these tiles are black, then we would erase them by erasing this whole block. So we used one erase here, and we go up to here, and we see it's white, so we go here. Okay, it's black, we need to erase here. We can also erase the next two blocks, but this is the end of the array. So this is our second erase. So this example is pretty easy since we just used one erase. We didn't end up skipping over any black tiles, but if I give another example, like the second example is, let's see, 1, 2, 3, 4, 5, 6, 7. This one is black. This tile is black. So k equals 3 again. White, white, black, erase this whole block. Then we just start looking here, because we don't need to worry about this block or this block, no matter what color they are, because we just use one erase to erase this whole block. White, white, done. Return 1. So I'll pull up my code here. So we, this is still C. So we read in the string, this is our current pointer, and this is our number of erases we've used. So we iterate over the array. If we see a black tile, we use an erase. We also just jump ahead k, since we don't care about any of the k blocks after or k minus 1 blocks after we erase, since those blocks will also get erased no matter what. In the case that it's white, we just move on, we don't do anything, and then we just output the number of erases we do. So pretty simple. We can see that we would need at most n minus k erases rounded up, so I'll use 7 as a good example. So k equals 3. 1, 2, 3, 4, 5, 6, 7. So let's say they're all black, which is the case where we would need the most erases. We start here. This one is black, so we erase this whole block. We go here, so this is 1. This one is black, so we erase this whole block. 2 erase. Go here. This needs to be erased. 3. So 7 over 3 rounded up is 3. So O of n time, because we need to scan the entire string to see if there are any block tiles. O of n space, since we read in the string all at once. As with a lot of these problems, there's probably some way to read in the string one character at a time, so you can do it in constant space, but we have plenty of memory for our event. All right, fifth problem. Building an aquarium. So there's a few ways to do this. I saw a solution where it sort of computes the answer directly, but the solution I'm going to present uses binary search. I think it's just as efficient, but it's also simpler and more intuitive, in my opinion, to understand and implement. So we can see that if we raise the height of the walls, of the tank walls, we will use the same amount of water or more, and if we decrease the walls, we will use the same amount of water or less. So we can perform binary search on the height of the walls, and then whenever we have a guess for our binary search, the middle point of our search range at that time, for the wall height, we can just directly compute the amount of water we use, and then check, is this too much water? If it is, then we throw away the bottom half of our wall height search space. We do that if it's too little water. If it's too much water, we discard the top half of our height search space. If it's exactly correct, then we return that height immediately. So we need to figure out what our range is, our search space is for the height of the wall. So the minimum wall height is 1, because if the wall height is 0, then we would never add any water, and we know that we'll always have to use some water. So it can't be 0. So the minimum is at least 1. And the maximum is 2e to the 9. The reason why that is because there's a case where we have one column in the tank, where the height of the coral is 10 to the 9, or 1e to the 9, and we need to have also 1e to the 9 water. So this is with 1. So then the height of this wall must be 2e to the 9. And this case exists, we can see, because the height of the coral can be 10 to the 9, and the number of the amount of water could be 10 to the 9. So this case is possible. So our height wall maximum is at most this. So in my code here, I used int max for simplicity, but this is somewhat close to 2e to 2e9, so that will work just fine. When we take the midpoint of our current search space, we iterate over the tank left to right, keeping a count of the water used. So for each column, the water for that column is as follows. If the height of the coral is greater than the height of our walls, so if mid minus AI is negative, then we don't add any water. Otherwise, we add whatever the difference is. So we just add that to our running sum. If we somehow stumble on the exact amount of water, then we know this is the best height, since we're trying to maximize the amount of water without exceeding it. So in this case, we return mid. It's actually, now that I think about it, if we increase the tank wall height, we'll actually always increase the amount of water. It won't stay the same, I think. Otherwise, we would have to check later or higher wall heights, because there could be some height like mid plus 1 that has the same water. So my statement earlier was actually incorrect. If we lower the wall, it will strictly decrease. If we raise the height of the wall, it will strictly increase. So if we get the exact amount, then that's definitely our answer. If we have too much water, we discard the right side of our search space. If it's not enough, we discard the left side. And the reason why I set R to mid is because this binary search is actually slightly modified. This binary search finds the lowest number that doesn't work. So the first number that exceeds the threshold. It's just more convenient to do it that way, since if you try to find numbers that or wall heights that do not cross the threshold, you eventually have to iterate upwards to find where the boundary is. But with this way, you can just have your right pointer always be the lowest value you've seen so far that exceeds the threshold, and eventually it will be the lowest value in general that exceeds the threshold. And since R is the first value that is too big, we just return R minus 1. So this runtime is O of n log int max. That's because our search space at the beginning is int max minus 1, so we'll take log of int max rounds of binary search of this loop running to terminate. Each round of binary search, we iterate over the width of the tank to compute the amount of water. So we iterate over like this and calculate n columns worth of water. So n log int max total, we need O of n space since we are storing the heights of the coral columns in the tank. Yeah, that's all. So next problem, F, money trees. So in my opinion, this is the most complicated problem, especially when it comes to implementation. So this problem will have two steps, a two-pointer step and a binary search step. So the overview of our strategy in this problem is we need to partition the tree into groups using this divisibility rule. Then each tree will be in exactly one interval. No more, no less. That interval might just be a single tree. So that's the two-pointer step. And the reason why we're doing this is because we can only collect fruits from one interval. So if we divide them up into intervals, then we can visit each interval one by one and then pick which one is the best. So we'll get to how to exactly implement that in a second, but that's the first step. The second step is for each interval, we need to find the sub-interval that gives us the best result, maximizing the amount of fruit we get, but not exceeding the limit. So we can't just automatically take all the trees in the group, because if we do that, we might go over the limit and get caught. So we need to choose the optimal sub-interval for this interval to get the most fruit without exceeding the limit. And that is our binary search step, and I'll elaborate on how that works. Before we continue, we will also compute a prefix sum of all the trees. So this array here, array A, and we'll see whether it's useful later. So step 1 is to find an interval, and then we will perform step 2 on the interval, binary search, and then we'll move to the next interval, or we'll move on to finding the next interval, step 1, and then do step 2 on that interval, and so on and so forth. So in order to do step 1, we need to have a left pointer and a right pointer. So this is our prefix sum here, read in the heights. If there's only one tree, then if that tree is over the maximum, we can't harvest anything. Otherwise, we can do one tree. So I think it's asking for the maximum number of trees we can harvest from. So this is a special case if there's only one tree. Anyway, 2-pointer step. So we begin at the beginning. So this is one index. We start at the beginning and we iterate left to right. Our left pointer will stay where it is for now, and our right pointer will walk. So if this else statement is if the next number if the number we're looking at is divisible, or if the previous number is divisible by the number we're looking at, then that means we're still in the same interval. It means these two trees are in the same group. So originally my left pointer is here, my right pointer is here, so I go right. Okay, this follows the rule, so that means these three trees together are a group. Then I check this one. It breaks the rule since 2 is not divisible by 4. So I say, okay, this is my first interval. Then I would do my step 2 on that. So step 1, when we find the end of the interval. Step 2, binary search. So the way we do our binary search is that we introduce another 2 pointers. So our first pointer is going to be the start of our subinterval, not the start of the whole interval here, the start of our subinterval. And we're going to check every subinterval starting with this one. So we put our subinterval left here, and we use binary search to find where the right side of the subinterval should be. And that's where our prefix sum comes in handy, because so this is the subinterval left. It's wherever I is, since we're iterating over all possible starting positions for our subinterval. Our subinterval right pointer, and this is where we're going to be using binary search to find. We do binary search if this subinterval doesn't have enough fruit, or it doesn't exceed the limit, then we or rather, this is the yes. This is initially initially the search space for our right side of our subinterval. Sorry, this is the left side. So we do binary search to find what the right side should be if there's not enough fruit. So our subinterval right now is from I to mid. If we can get more fruit, then we shorten our search space to the upper half to try to get more fruit. If we have too much, then we discard the top half of our binary search space. And this is if they're equal. So if fruit is equal to k, it means we found some subinterval that gives us the maximum amount of fruit, which means we're done looking at this interval. So so this is our interval length. If our interval length is better than what we've seen so far, update it. Okay. And we need to do this for every subinterval in our interval, because even if we find a subinterval that gives us the maximum amount of fruit, there might be another subinterval within this interval that gives us the same amount of fruit, the maximum, but it's longer. And we need to find the maximum subinterval that gives us as much fruit as we can get. So we keep track of the best interval here. And once this terminates, we bring our main left pointer up to our right. So when our first interval was here, our left pointer was here, our right pointer was here. When we're done doing binary search, we bring our left pointer up here to meet our right pointer, and then our right pointer can continue walking rightwards, and we just repeat. And we do this process, actually this is along a subinterval count. So the time is n log n, and the reason why that is for each interval, let's call it k. So in this case, we had two intervals, one with 3, one with 2. For each interval, we need k log k time. The reason why that is because we need to check every starting point for a subinterval. So our subinterval left pointer was going 1, 2, 3, 4, 5. So there's n starting points, and our binary search, which was searching for the right side of our subinterval, was needs log k time to find it, since we're binary searching over the rest of the array, or the rest of the subinterval. So that takes log k time. Finding the left pointer takes O of k time. So we need to do binary search for every starting point. So that's a total of k log k. And this means our total time is the sum of all the k log k's. So in this case, it would be 3 log 3 plus 2 log 2, etc. So the worst case is actually if all the trees, the entire row, is in one interval, and we have one interval of n log n. I'm not going to prove it, but with a quick example, this might be able to convince you. Imagine we have two intervals of n over 2. Then our runtime for both of them is k log k. K is n over 2. So we have n over 2 log n over 2 plus n over 2 log n over 2, which is n log n over 2, which is less than n log n. So by dividing our by having two intervals of half each instead of one full interval, our runtime decreased. If we have m intervals of size n over m, our runtime would be n log n over m. So you can fiddle around with that if you want to convince yourself further that the worst case is one interval containing all the trees, but it is n log n in that case. We use O of n space since we store a few different arrays. So we store the fruit on each tree, we store the height of each tree, and then of course we compute our prefix sum. And our prefix sum allows us to find quickly the amount of fruit in any subinterval, since we just check the amount of fruit, or the prefix sum of the fruit at the end of our interval minus the beginning of our interval, and that's how much fruit is in the interval, subinterval. Okay. Gee, so this is an interesting problem. I think in some ways it's actually easier than it seems. So we'll begin by saying if we convert an AB into a BC, if there are more A's directly to the left of the AB that we turn into a BC, we can continue doing these conversions until we run out of A's. So there's an example. We initially start with this string. We convert this AB into a BC, and there's more A's on the left, right? So we can continue shifting this BC downwards and consuming these A's to convert them into BCs. Eventually we run out of A's and then we're done. So in this example we consume 3 A's, we get 3 points. Similarly, if we convert a BA into a CB and there's more A's on the right, we can continue doing this as well. So we convert this into a CB here. Then we can convert this into a CB. Then we can convert this into a CB. So we consume these 3 A's. So basically, in essence, for every B, we can choose a direction left or right. So in this example, we chose left, since there's A's on the left. This example, we chose A's on the right. And go in this direction, consuming A's, until we run into a B or C or the end of the array. And we can't do anything with BB, CB, BC. So the problem can be thought of, how can we consume as many A's as possible? Since 1 A is needed for every operation, the number of A's that we consume will be the number of coins we obtain at the end of the problem. So another way to look at it is like this. There's some number of A's in the string, so we can't get more coins than that. Also, these A's are divided into clusters by B's. So in this example here, there's a cluster of 2 A's here and a cluster of 1 A here. And they're divided up by these B's in between them. So if there are y b's, then there must be y plus 1 clusters of a's, including empty clusters. So the reason why I say there's 3 clusters is because there's 2 b's, so there's 3 clusters. This is one cluster, this is another cluster, this is another cluster, but there's another cluster here before the b that's an empty cluster, that endpoint. So there are 2 b's, so there must be 3 clusters, even if some of them are empty. If we had a two consecutive b's, like here, there's still 3 clusters. One here, an empty one in between them, and then an empty one here at the end after the last b. So we've already determined that a particular b can only go in one direction once it starts going in that direction, and it can't change direction because it left c's behind it when we transformed. So when we were going left here, we were leaving behind more and more c's on our right. Similarly, when we were going right, we were leaving c's in our wake on the left. So if we have y b's and y plus 1 clusters of a's, we can just take all the clusters except the smallest one, and we just ignore the smallest one in order to maximize the number of a's we can consume. We can always choose to ignore one cluster and take the rest, since the b's on either side of that cluster we're ignoring will both traverse away from that. So I can show a quick example here that will illustrate this. So if we have this string, clearly in this example this b should go this way, this b should go this way, and then I would end up with so these b's are traversing outwards because the cluster here is 3, 1, 3. So we have 3 clusters, 3, 1, 3. We want to pick the 2 biggest clusters since we have 2 b's, so we pick 2. We ignore the minimum one. So you can convince yourself that no matter what the string looks like, we can always ignore. If we find the minimum cluster, we can always ignore it. So even if it's 0, like this, cluster of 3, cluster of 3. This is technically a cluster of 0. So we have 3, 0, 3. Clearly we want to ignore this and just take these 2. So this b goes this way, this b goes this way. So we iterate over the string. Iterate over the string. If we see an A, we add it to the streak, because since we're counting cluster length, we need to find the number of consecutive A's that we've seen in a row. If we see a B, we end the cluster and we see, okay, is this cluster the smallest we've seen so far? If it is, we update our minimum, and then we update our sum with the total length of this cluster. Because at the end, we want to have a sum of the sum of all clusters of A's, which is the total number of A's in the problem. We also need to check here at the end, because we could have an example like this where when we get to the end of the string, we still need to record this streak of 3 in this example. So we just record it again at the end. Then, like we said, our answer is going to be all of the A's minus the smallest cluster. So sum, which is the total A's, minus the smallest cluster, and we're done. The time it takes is O of n, since we simply need to iterate over the string one time, checking for our clusters of A's. Our space is O of n, since we store the string. Like a couple of the other problems, you might be able to read it in one character at a time and get O of 1 space. Alright, the last problem. Mad City. So this is a pretty interesting graph problem. Before we begin the strategy on actually how to solve it, we're going to build our graph using the edges given to us, and we should use an adjacency list since the problem statement tells us there's exactly n buildings and n two-way roads. So this is undirected graph with n nodes, n edges. So n nodes, n edges tells us we should use a sparse graph. So an adjacency list. We're also going to main two distances for each node. So in my code, I have it as vis1, vis2. So this is our adjacency list graph. And what this distance is going to represent is the distance that Valeriu and Marcel each start from. So if vis1 of 10 is 5, it means Valeriu started 5 distance away from node 10. And then the same with Marcel for vis2. We'll initialize them at the start with some sentinel value just to signify that this node has not been visited yet. Okay. And then as we traverse in our searches here, then these values will get updated with the proper distances. Okay. So now into the actual conceptual strategy. There's exactly one cycle in this graph. And we know that because if our graph has n-1 edges and n nodes, then assuming the whole graph is one connected component, which it is, any pair of buildings connected by some path, so we have one single connected component. So the graph is not multiple disconnected components. A single connected component graph with no cycles will have exactly n-1 edges, but since we have n edges, it means we added an extra edge and created exactly one cycle. So because of that, the implication is our graph looks something like this. There is some cycle, and there's a bunch of like branches hanging off of it. So these branches can be like however complex, but there will only be one cycle in the middle. Okay. Okay, second observation. If Valeriu can reach a cycle without being caught by Marcel, he can evade him forever by running around the cycle. So in the example they give here, if Valeriu starts at, 1 here, and Marcel starts here, if Marcel moves here, Valeriu will moves up to 3, Valeriu will move down to 2. If Marcel moves up to 1, Valeriu will move up to 3. So they can essentially play ring around the rosy like forever if Valeriu can get to the cycle without getting caught. That part is pretty simple to see, I think. Obviously, if both of them start in the same building, no matter what else happens, then Valeriu is instantly caught and we just return no. But that's a special case. So essentially, our thought process is the following. If Valeriu and Marcel start in the same building, which is the first thing we should check, Marcel wins, which corresponds to a no answer. An answer of no. If they're not in the same building and Valeriu starts in a cycle, then Valeriu wins. Because if he starts in the cycle and he doesn't get caught immediately, then he can escape forever. So if that doesn't happen, the next step we go to is if Marcel can intercept, so Valeriu he doesn't start in a circle. And Marcel can intercept Valeriu before he enters the cycle, or if he can intercept him as he enters it, Marcel wins. Otherwise, if none of these cases are true, Valeriu wins. The last case is the case where Valeriu is not inside the cycle at the beginning, but he can get there. He can get inside the cycle before Marcel can cut him off. So the first condition, this one is trivial to check. We just check if the start points are the same. Otherwise, we go to the next condition. So we check, is Valeriu starting in the cycle? So in order to pull this off, we will do a depth first search. So I have that here. And we will start on the building that Valeriu starts in, and we will mark the distance from his start node to each node we visit. So we just traverse the graph, and if we visit a previously visited node, we do not overwrite the first distance, because we want to see the earliest distance we write will be the true distance, the shortest distance from Valeriu to whatever node. And when we encounter a node that we are visiting, and we see that one of its neighbors is a node that we already visited, then we found the cycle as long as that neighbor was visited more than one time step ago. Otherwise, like in this example, if we do a depth first search starting on 2, we go to 1. 1 is neighbored with 2, and we already visited 2, but that doesn't necessarily mean we found the cycle until we find 3. But if we go 2, 1, 3, and 3 is neighbored with 2, then we found the cycle. So in the code, that's if U is partnered with, so V is a neighbor of U, V has already been visited, and it was visited longer than one time step ago. So this means we found the cycle. What's even more significant is that it means this node V is the entrance to the cycle that Valeriu this is the entrance Valeriu is going to use. So if he's not in the cycle already, he's on one of these branches, and all these branches only have one point which you can enter the cycle on. So if Valeriu is not in the cycle initially, our DFS will return whichever entrance he's going to use. If he's already in the cycle, then so the reason why our DFS will work that way is if, let's say we started like here, our DFS would quickly find this dead end, and then we would go like this. And we would get into the circle, visit this point, and we would walk around here, and sometimes we would check these dead ends, sometimes we would pass them, but whether we check these dead ends or not, we would eventually get back here, and we say, oh, we were already here before, so this is the entrance that we need to use to get to the cycle from this branch. Now, if Valeriu is already in the cycle, so let's say we start like here, we still do a depth first search, and then once again we'll walk through here. Some of these dead ends we'll end up exploring, but ultimately, eventually we will get back here, and if we end up on the same node, if we detect the cycle on the same node that we started at, it means we're already in the cycle. So that's how we find the cycle and our distance to it. So if the cycle detection gets triggered on the start node, that means we're already in it. If everything starts in the cycle, V, which is the entrance to the cycle, will be B, which is where Valeriu starts. Otherwise, it will be the entrance to the cycle from whatever branch Valeriu starts on. Okay. So we already checked this, and then now we can check this. So if it turns out Valeriu did start in the cycle, then we can immediately answer yes. But otherwise, we need to find if Marcel can intercept Valeriu in time. Okay. So in order to do that, we already know which entrance Valeriu is going to use. So we're now in the case where he started on a branch. So let's say we started here, and this is the entrance he's going to use. Let's say Marcel started here. what we care about now is how long does it take Marcel to get from his starting point all the way to this entrance. Because if he can meet him at this entrance, or get there, if Marcel can meet Valeriu at that entrance, or get there before him, he will win. He will be able to stop him, to catch him. So we need to find the distance from here to here, and we can do that with breadth first search. So breadth search first checks all the nodes that are one distance away from here. So that would be like here and here. Then it checks all the ones that are two distance. So here, 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 here. Then 3. So here, 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 here. Then 4, here, 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 here. 4. So this is a standard breadth first search. We have a queue of visited nodes. When we visit a node, we add all its neighbors to the queue, all its unvisited neighbors to the queue, and then we process them first in, first out. And if we ever find the destination, which is the entrance to the tunnel, or the entrance to the cycle, that Valeriu is going to use, then we return the distance that Marcel is from it. So in this case, this distance 1, 2, 3, 4, 4. I guess I haven't really drawn vertices or edges in here, but let's say we estimate this is 2. So then Valeriu can get here into 2 and be inside the cycle before Marcel gets here. So in this case, he can circle this forever, and our answer would be yes, since Marcel cannot intercept Valeriu before he enters the cycle. So if you are not familiar with DFS and BFS, you should have a look into that. Once you are more familiar with that, you can read these search functions and it will be fairly clear on how they work, especially with the comments. So our distance is, did we start in the cycle? For Valeriu, his distance is, if we start in the cycle, our distance is 0. Otherwise, it's the distance to the entrance. So the entrance is Vis1, Vis1b. So Vis1, Vis1b is the distance to the entrance from where Valeriu started. And Marcel's distance is the result of our BFS from his starting point until whichever entrance we were using. And we simply compare them. If Marcel's distance is less than, that means he will get there before him and he can just gatekeep the entrance to the cycle. If Valeriu does not enter the cycle, then Marcel can eventually corner him in that branch. If it's equal, that means they'll meet at the entrance at the same time, and that's classified as Marcel capturing Valeriu. However, if Valeriu's distance is less than Marcel's, then he can get to the cycle before getting intercepted and then evade capture forever. So the time it takes for us to run this algorithm is, or this code is O of n, since building our graph takes O of n time, since we take in exactly n edges. DFS and BFS each run in O of v plus e time, which is vertices plus edges. In this problem, they're both n, so both O of n. And the amount of space we use is an adjacency list, which takes O of v plus e space, since we have one entry per edge, as well as one list per node, so v plus e. Again, that's also O of n space. We also maintain our distance tables, which are both O of n space as well, so our total is O of n. So that's going to conclude it for this video editorial. As usual, this document is going to be linked in the description. If you have any questions, feel free to leave a comment on the video or message me directly on Codeforces, and hopefully this video was helpful.